Hello. All right, chapter 7. Recurrence relations. Okay. All right, so here this section will have a bunch of examples, and then we'll use these in the future to study certain aspects of discrete mathematics, I guess. So here we go. So here's an example. Suppose we start with 5, and then given any term of a sequence, right? So we're generating a sequence. We want to add 3 to it. So we can write that sequence down right here, right? That's what it would look like. Okay, and another way of doing that, we could rephrase this entire example by saying, let's let A1 equal 5, right? And then you replace instruction 2 here, right, to add 3 to that by this equation right here. AN, the next term, is always equal to A sub n minus 1 plus 3. So that's an example of a way of expressing a recurrence relation. And so taking n equal 2, you see we get 8. N equal 3 gives us 11, right? And we have to know the value of the previous one to get the new one, right? And so that's an example of a recurrence relation, okay? So here's a definition, right? A recurrence relation for a sequence of numbers or whatever, of anything, is an equation that relates an to certain of its predecessors, right? So the idea is that once you know the first one, you can find the second one. Once you know the second one, you can find the third one because it's going to be a function of the previous two in some way, right? So that's what a recurrence relation is. Some examples that we are familiar with through the course of the Fibonacci sequence is an example where Fn is equal to f sub n minus 1 plus f sub n minus 2 for n equals 3, and that generates our Fibonacci sequence, right? If we start with the initial conditions of f1 equal 1, f2 equal 2, then we can generate Fn, okay? If we were to change the initial conditions, we would get a different sequence, right? So, all right, here we go. Here's another example. The idea here is we're going to invest $1,000 at 12% interest compounded annually, okay? And if A sub n represents the amount at the end of n years, then we want to find a recursive relationship and an initial condition that defines the sequence A sub n. So they're claiming, well, here, this is how it works, right? So what you do is A sub n is always you take the amount that you had at the end of the last year, A sub n minus 1, plus 0.12 times A sub n minus 1. So if you do a little algebra, you get that's 1.12 times A sub n minus 1 for n greater than or equal to 0. Now, to apply this recurrence relation for n equals 1, we need to know, right, the value of A0. And we are given that value as 1,000. So A0 is 1,000, right? And using this initial condition, watch what happens. We can see that A3 is A1 times, is 1.12 times A2, which is 1.12 times 1.2, is 1.12 times A1. And what we can see is that we can represent A3 is actually equal to 1.12 cubed times 1,000. So in general, what I guess what they're pointing out here is that we can actually get an equation that tells us exactly A sub n equals that number to the n. So that's a function of n. Okay, so a little bit different deal there, right? All right, here's another example of another relationship. Now this is so let Sn denote the number of subsets of an n element set, which we know is, we know the equation for that. But what we also notice is that since going from n minus 1 element set to an n element set, we double the number of subsets, right? That's the idea. We know that from this theorem that we went over, that the number of it's 2 to the n, right? So we can do it this way. Sn is equal to 2 times Sn minus 1, and the initial condition is that S0 is equal to 1. If you track that through, you can then solve and realize that Sn is actually 2 to the n. Okay, here's another example. This one's kind of interesting, and this is more in the spirit of what we're going to be going into in the future. So let's let Sn denote the number of n bit strings that do not contain the pattern 111, okay? And we want to try to develop a recursive relation for S1, S2, et cetera, et cetera. So here's a little strategy. They looked at this, and we want to divide the numbers in Sn into A, the ones that begin with a 0, B, the ones that begin with a 1, 0, and C, the ones that begin with a 1, 1. And we'll see why we're doing that in the future. Well, actually right now. So let's take a look at number A. So if a sequence starts with a 0, right, and we ask that it does not contain the numbers 1, 1, 1, right, well, that must have occurred. There's exactly S sub n minus 1 of those, right? So that's where this term comes from, right? That's for the parts that are in A. Now, so we're going to add those. And notice that if the sequence in Sn starts with a 0, it certainly doesn't start with a 1, 0. So now we're going to consider all of the sequences that start with a 1, 0, right? And if you look at that, so if it's a sequence that does not contain a 1, 1, 1, all the ones that occur there, they also don't contain a 1, 1, 1 if they're part of Sn minus 2, right? So that's why we have to add in this Sn minus 2. And similarly, if it begins with a 1, 1, 1, right, then let's see, we're looking at the following sequences, right? So if it doesn't start with 1, 1, 1, then let's see what they're saying here. I'm having a little brain fart. So if we do that, then look at what's beyond that. If we put a 1 there, that's why it looked a little confusing to me, but we would have to have a 0 starting right there. Otherwise, it would have a sequence 1, 1, 1. So if there's a 0 there, and then you look beyond that, you would not see any. You would not see a 1, 1, 1. So that means that every string that begins 1, 1, and then you'd have to have a 0, has to be followed by a sequence that has no ones from Sn minus 3. And that's where this comes from. So the formula is right here, that you can actually now generate these numbers. So by inspection, we find that S1 is 2, S2 is 4, and S3 is 7. So that gives you a way of finding all the rest of them, right? You could, for example, S8 is just what you get when you add up like 7 plus 4 plus 2, right? Yeah, 13, and so on and so forth. So these are just some examples in 7.1 to get used to this idea of this recursively defined objects, right? And here's a really interesting one and a kind of historically important example. Okay, the Towers of Hanoi. So here they are. I'll explain the game and I'll talk about what we're trying to do here. So the idea is that you're allowed to move these pegs, or the game is to take all the pegs here and move them to a different peg where you still have the largest one on the bottom and they continuously get smaller. And the rules are that you cannot put a larger peg on top of a smaller peg. So for example, you could take this first peg, move it over to 2, then you could take the second peg, move it over to 3, and only then can you take this peg from 2 and put it on 3, and then maybe move another one. So you're trying to move them so that you're never putting a larger peg on a smaller one. And so what's the question here? So we want to find an equation for how many moves. Well, first off, can it be done? And secondly, we want to find a recursive relation that tells us how many moves occur, okay? So here we go. Let's start. I'll just start like reading here. So we give a recursive relation. If there's only one disk, that's pretty. So this is like induction, right? If there's only one disk, we simply move it to the desired peg, right? If n's greater than 1, then disks. If n is greater than 1, then disks on peg 1. See this figure here, right? Like this, right? So suppose it looks like this. Okay, we begin by recursively involving our algorithm to move the top n minus 1. So we invoke, using like sort of a hypothesis, using our sort of inductive assumption, let's move the n minus 1 disk to peg 2. Okay, so in other words, we use our n minus 1 to move it here. Okay, so there we have it, right? So now what do we do? Okay, so if n is greater than 1, so we solve the n minus 1 disk problem twice, right? Because what do? We put these n minus 1 disks here, and then the idea is we'll move this disk over here, and then we'll resolve the n minus 1 problem here again. So what does that say? And then, so what did we have to do? So when we move from here to here, we solve the n minus 1 disk thing. That's n minus 1 moves. Then we move one more, and then we did the n minus 1 thing again. So that tells us that right here that, in fact, C sub n is 2 times C sub n minus 1 plus 1, okay? So now the question is, that tells us how to do it. It's sort of an inductive recursion that once we know how to solve the previous problem, then we do the second one. So, for example, if we had 2 disks, we'd move the little disk here, the big disk would then be moved to 3, and then the little disk would go over there. So that's 3 moves, just like it's supposed to be, right? Okay, so we can actually show that C sub n is 2 to the n minus 1, okay? Well, that's pretty clear because let's just take a look. We know that if you just start with C1, right? C1 is 1. C2 would be 2 times 2, right? Then 2 cubed. So it goes on, and that's clearly the formula, right? Now, here's another interesting thing. Let's let D sub n be the number of moves in an optimal solution. So we can even do a further analysis of this. Maybe there's a better solution than the one we found, right? So let's use mathematical induction to show that, in fact, C sub n equals D sub n. Okay, so let's do it. Okay, by inspection, if C sub 1 equals D sub 1, that's pretty much the optimal solution, right? So let's, the inductive assumption, let's assume that it's true for n minus 1. In other words, we're assuming that C sub n minus 1 is equal to D sub n minus 1. And now let's consider the point in the optimal solution at the n disk problem, right? When the largest disk is moved for the first time, okay? So there is a first time when the largest disk is moved, right? And so when you move it, right, it has to be moved to an empty peg. So essentially, the picture has to look like this at some point, and then it moves over, right? So what's the big deal? Well, in other words, the n minus 1 disk problem must have been solved, right? And let's suppose that it was solved with D sub n minus 1 moves. Okay. Well, then we can absolutely know that D sub n is greater than or equal to 2 times D sub n minus 1 plus 1. But by our inductive assumption, D sub n minus 1 is C sub n minus 1. So that says that D sub n is greater than or equal to 2 times D sub n minus 1 plus 1. That's equal to 2 times C sub n minus 1, but that's equal to C sub n. But you see, C sub n is supposed to be the minimal one. So that means D sub n is equal to C sub n. Okay? It's kind of a subtle thing, but that's another example of a recursive relationship and how we can get it to use to see how it can help us to solve certain problems. So, okay, well, that's basically all I wanted to cover in this section. So I hope this helps you out. Thanks.